In section 3.3, we continue to look at probabilities of two events. First, we need to know when events are mutually exclusive or not. Notice our definition here. It says two events are mutually exclusive if they can't occur at the same time. For example, let's consider asking everyone in the class what their status is as far as classification at SWIC. Depending on the number of hours you've completed, maybe you're classified as a freshman, or maybe you're classified as a sophomore. Would the group of people who are classified as a freshman overlap with the group of people who are classified as a sophomore? Or would they be two totally separate groups? If we're talking about how many credits you have right now, classifying you as a freshman or a sophomore, that would make two totally separate groups. At this given time, either you're classified as a freshman or you're classified as a sophomore. You can't be classified as both at the same time. On the other hand, if we asked everybody in the class if they were a fan of Cardinals baseball and or Blues hockey, those two groups could overlap. Someone could be a fan of Cardinals baseball and Blues hockey at the same time. These diagrams we're looking at are called Venn diagrams, and that's a good way to see a picture of whether events are mutually exclusive or not. In the next couple of examples, we have two events that we want to consider and decide if these two events are mutually exclusive or not. In our first example, we want to think about rolling a die. Imagine getting an even number and what all rolls that would include. And imagine getting a number less than 3, what all rolls that would include. We want to think about if these two groups are totally separate or if there would be some overlap. Even number on a die, let's see, rolling a die, we could have a result of 1, 2, 3, 4, 5, 6. So even numbers would be 2 or 4 or 6. A number less than 3. Less than 3 means it has to be smaller than 3. That would be a 1 or a 2. It looks like the number 2 did come up in both of these groups. So thinking about that Venn diagram, these two events would overlap. 2 is a part of both of them. Even numbers would include 2, 4, or 6. Numbers less than 3 would include 1 or 2. Since there is overlap, that means that they are not mutually exclusive. Let's say we were talking to registered voters and asking them if they were registered as Republicans or Democrats. At any given time, could someone be registered as both a Republican and a Democrat, or would these be two totally separate groups? When you declare your party affiliation, it's going to have to be one or the other. So Republicans and Democrats would be two separate groups. That means that, yes, those events are mutually exclusive. Let's say we're selecting a student from SWIC and we're interested in knowing if that student is a sophomore, and we're interested in knowing if that student happens to be a business major. Would the group of sophomores and the group of business majors overlap at all? Or would they be two totally separate groups? There definitely could be a student that's both a sophomore and a business major. Since these do overlap, that means no, they are not mutually exclusive. Take a minute to pause the video. Try deciding if each of the following are mutually exclusive, and then check back in to see if you get the right answers. So if we randomly select a psychology major, could that student be male and 20 years old at the same time? Those groups would overlap, so this would not be mutually exclusive. Thinking about randomly selecting a student and checking on their birthday, Students with a birthday in April, students with a birthday in May, could those groups overlap? No, they'd be totally separate groups. So that makes them mutually exclusive. Thinking about selecting a member of Congress. The group of female Congress and the group of senators could definitely overlap. So that means they are not mutually exclusive. So whether events are mutually exclusive or not helps us know what version of the addition rule we need to use. When we're asked to find the probability of one event or another, or is a keyword meaning that we should add those probabilities. So addition rule, one event or another, we're going to add the probabilities. The thing we have to keep in mind though is when events are mutually exclusive, meaning they're two completely separate groups, there's no overlap. So there's no risk of double counting when we add those two probabilities together. On the other hand, if we don't know that the events are mutually exclusive, we have a more general rule that would apply when the groups do overlap or could possibly overlap. And the problem is when we add the probability of event A to the probability of event B, the items that are in both A and B get double counted. So we're going to actually subtract off the probability of that overlap to eliminate the duplicates. If we have included something in group A that was also in group B, they've been counted twice. So subtracting that one item back off will eliminate the duplicates. Let's see an example of the addition rule in action. The example below says the estimated distribution of the U.S. population for the year 2025 is shown in the pie chart here. Then we're asked to find the probability of each event. Like in part A, the probability of randomly selecting someone under 5 years old. Let's start with a little bit of notation. P to show we're finding the probability, and under 5 years old to describe the event that we're interested in. And then let's look up at the pie chart and see how many of the pieces or slices of pie would be included. Looks like under 5 years old is its own slice of pie. So if we'll just change that 6% into a decimal, or in other words 6% divided by 100, we'll know the probability. So 6 divided by 100 gives us 0.06. That was what they call a simple probability because the event only included one slice of pie. On the other hand, part B wants us to find the probability of randomly selecting someone who's 45 or older. And if we look at the pie chart now, 45 or older, that includes 3 slices of pie. Probability of 45 or older. We need to then decide if those slices of pie overlap one another or not, or if they're totally separate. If they overlap at all, we would need to do some subtracting after we add all the probabilities together. On the other hand, if they're totally separate, we can just add the probabilities together. Looks like in this case there's no overlap. This group goes from 45 to 64. The next group starts at 65. Since they are totally separate, we can just add those probabilities together to get our total result. So starting with the 23.6%, let's change that to a decimal. Or 10.7%, let's change that to a decimal. Or 8.3%, let's change that to a decimal. And since we're looking for the probability of OR, we're going to add all those together to get our final result. 0.236 plus 0.107 plus 0.083. Total answer 0.426.